This is video 2 for week 8, and we're working on network clustering. We want to define what we mean by cohesiveness. If 2 vertices are in the same cluster, that means they're likely to be connected than if you just pick 2 vertices at random. So you could say that 2 vertices are adjacent if they're similar under the relationship that you've defined to create the network, and so that all of the vertices in the same cluster are somewhat similar since they're more likely to be connected. So we call this property of similarity within the same cluster as cohesiveness. In looking at clustering, we also may note that we have 2 different types of clusters. We could have a clustering algorithm that partitions the vertex set. We call this a cluster partition. And then our clusters do not overlap if we have a cluster partition, and so we have what is called exclusive clustering. On the other hand, it is possible that we define our algorithm, and we'll see examples of each, where our clusters do overlap. And so this type of method would give us a cluster cover, and the method is called overlapping clustering. And the big question that we want to address is, how do we find these clusters? Well, we still need to talk about our objective before we talk about the different types of algorithms for finding clustering, because there are 2 basic kinds of objectives. We define what we mean by cohesiveness, that we want the vertices in the same cluster to be similar, and therefore that's another way of saying we want the clusters to be dense. And is that our primary objective, to maintain a level of density within each cluster? Or is it more important to us to restrict the number of clusters? We don't want too few, we don't want too many. So that could also be driving the clustering algorithm. So how do we find a cluster in a graph? We can think of a cluster, as I said, as a dense subgraph. And so one method of defining a cluster is called the clique-based clustering algorithms. We've already seen an algorithm where a greedy algorithm where the algorithm returns a maximum independent set, which is really the opposite of a clique, right? An independent set induces no edges, and a clique, every possible edge is there. Well, you could flip the result. So if you consider the complement of the graph, that if you have an independent set in a graph, then it is a clique in its complement. So sometimes a network can be represented as a complete graph. The underlying network, G, and its complement are represented at the same time, which would give you a complete graph. So if you think about, for example, we're going to look at the protein graph, where every vertex represents an amino acid, and 2 vertices are connected if they are within a distance threshold. Otherwise, they're not connected. Well, that's a choice. You could choose to connect every single vertex and then label the edge with a distance. And then you could use the algorithm to find, for example, a minimum or a maximum independent set, which would drive a clique in the complement. Now, if we have a complete graph, as I've described, where the edges are weighted, then the algorithm to find the cliques is to find cliques where the weight is either maximized or minimized. And in this case, you say a priori how many cliques you want. So the K clustering, min-max K clustering, you know how many cliques you want and how, given that many cliques, can you say minimize the edge weights within each clique? Why would you minimize them? Well, then you would, in the case of a protein graph, you would be minimizing the distance between every pair of vertices. So this is an example of where the number of cliques is taking priority, and then you can find a fixed number of cliques or a fixed number of clusters with a constraint that they have a minimum weight within each. The other type of clustering is center-based clustering rather than clique-based clustering. So let's look at this tree structure that we looked at before when we used it to model secondary RNA structure. In that lesson, we learned the domination number. So let's recall what the domination number is. The domination number is the cardinality of a minimum dominating set, where a dominating set is a set of vertices so that every vertex is adjacent to at least one vertex in the dominating set. So we have a dominating set here of size 3. The copper-colored vertices are a dominating set, since every blue vertex is adjacent to at least one copper-colored one. And it's minimum because we can't use fewer than 2 to achieve that goal. Now, how does this help with clustering? One algorithm is that we can associate with each vertex in the dominating set a cluster by taking that vertex and its closed neighborhood. So if we do that, we have 3 clusters, one associated with each vertex. So the vertex on the upper left, we've taken its closed neighborhood circled in red, and then we have a closed neighborhood circled in blue, and the third one circled in black. So this obviously gives us this, the way the algorithm was executed here is an overlapping set of clusters. Now, the center-based clustering algorithms do not have to be overlapping. Let's take another example. It will be easier to find, or perhaps more productive, to find clusters based on an independent dominating set if we do not want our clusters to overlap. So in this example, our 2 vertices in the dominating set are independent. Now we still have choices as to how we want to define the algorithm to create our 2 clusters. In the top example, what we've done is chose the vertex of minimum degree. We take it and its 2 neighbors, so the closed neighborhood, to create a cluster, and then the other vertex, its neighborhood, with what is left to create our second cluster, so we've removed the neighborhood first. In the bottom left, we've chosen the vertex of maximum degree, and we take it and its closed neighborhood and remove it, and then take the other vertex with what is left, its closed neighborhood in the graph that is left. And then on the bottom right is like our first example. We do not have to remove the vertices, so we can take each vertex in its closed neighborhood, and it might be the clusters overlap. So we're using a dominating set to help us find the clusters in a graph. Let's do another example. Let's do the case where we want it to be exclusive. That is, we don't want overlapping clusters. Since we have 3 vertices in the dominating set, then we will have 3 clusters. Choosing the first dominating vertex 1, we'll take the vertex 1 and its 3 neighbors, 5, 9, and 2 for our first cluster, and we will remove those from consideration. Since Peterson's graph has 10 vertices, we've removed 4, so we now have 6 vertices left. we'll take the dominating vertex labeled 6 and its two neighbors 7 and 10. Recall 5 has been removed. That gives us our second cluster, 6, 7, and 10, leaving the last vertex in the dominating set, 4, and its two neighbors, 8 and 3. So this is our example of creating clusters, or finding clusters based on a dominating set. And we can do either inclusive or exclusive, overlapping or exclusive. So, in summary, there are two types of methods. One is we're really interested in the number of clusters, say K clustering algorithms where we have predetermined K. And the other one is we do not restrict or put a constraint on the number of clusters. Rather, we want to maximize the cohesiveness within each cluster, which is another way of saying we want to maintain a certain level of density within each cluster, regardless of how many clusters that produces. And in order to achieve these two, we have two different methods of defining an algorithm. The two that we've talked about, one is based on cliques, and the other is called center-based, where you choose a vertex that's the head or the center and build from there.